So now we're working on question 2D, which is a question on UV-Vis spectroscopy. And so the figure below shows the layout of the components of a UV-Vis spectrophotometer. So here is the layout, right? We have a lamp, so that's our light source, and that's going into something here, that's I, that we don't yet know. And then that's going into 2, which we don't yet know, we have to identify. And then that kind of gets splitted off into the sample cell up here and another cell that we are yet to identify. And then everything now goes to the detector. It's a comparison of these, okay? That the detector is gonna show. All right, so we have to identify the components. So the first component, right, whenever we have a UV spectrophotometer, the first component here is gonna be our diffraction grating. Let's just bring that up. So this is gonna be our diffraction grating, right? One is our diffraction grating, and the purpose of the diffraction grating is that it's gonna take the light that's coming from the lamp and it's gonna select or only allow light from the whole range of UV-Vis or UV or visible regions to proceed forward, right? So I'm just gonna write that. Let me just put them on here while I'm naming them down there. That this is my diffraction grating, and that's what it does. It's kind of gonna select for the wavelengths that we want to go into the spectrophotometer. So that's our diffraction grating, right? So once the diffraction grating sends through the UV-Vis light, then it's gonna buck up on or meet up on a rotating disc. So 2 is gonna be our rotating disc, right? So that's 2. That's our rotating disc. So let me just populate that here. That 2 is our rotating disc. And what the rotating disc is gonna do, right? It will look something like this. Let me just get this shape here. So the rotating disc would be something like this, right? If we were to actually like think of what the shape is, it's a disc. Let me just like bring it over a little bit more, right? All right, so this is a rotating disc that's going to be here, and what it's going to do, it's going to rotate in such a way that, you know, it alternates between sending light up to the sample cell and down to this other cell. What is this other cell? That's going to be our reference cell. All right, so let me just write that right there on the screen. That 3 will be our reference cell. We're gonna need always our sample cell. That's our sample that's being tested. And we're gonna need a reference cell. And in the reference cell is where we're gonna have our pure solvent, right? We're gonna have a pure solvent. So we will get some reading for that. That's gonna go to the detector. And we'll get a transmission from here as well. And that's gonna go to the detector. And that's how we're able to generate our UV-Vis spectrums, okay? All right, so let me just populate that down here. That is my reference cell. So 1, diffraction grating, 2, rotating disc, and then 3 is my reference cell where my pure solvent will be. Okay, all right, so let's move on to the other part of this question now. All right, so let's move ahead. All right, so for question 2E now, we have a 1 centimeter cube sample of a solution of guanosine, and that showed an absorbance of 0.70 at 279 nanometers. So that would have been the wavelength that was selected for and sent through that diffraction grating and through the rotating disc, and that's what would have gone through to the cells, okay? And so given that the molar absorptivity constant is 8,400 dm cube per mole per cm cube, and the cell path is 1 centimeter, we're supposed to calculate the concentration of the guanosine solution, okay? So here's all we have. We have an absorbance, we have a molar absorptivity constant, and we have a path length. Whenever you see those 3 things and you're being asked to find the concentration, the strategy is always going to be to pull on Beer-Lambert's law. We're going to use Beer-Lambert's law, and Beer-Lambert's law says that A is equal to ECL, that your absorbance is directly proportional to the concentration of the solution. So this is the equation for Beer-Lambert's law. And these are what each of these variables mean. The A is the absorbance, which we have. The epsilon is the molar absorptivity constant, which we have. And then the concentration is C, which we don't yet know. And we know our cell path or path length is L, and that is 1 centimeter. That's what they told us. Okay? And so if we need to find concentration, our objective is to find concentration, then we're going to have to rearrange this equation here, making the concentration the subject. Okay? And so when I rearrange this equation to make concentration the subject, I'm going to come out with this, that the concentration is going to be equal to the absorbance divided by the epsilon, the molar absorptivity, times the cell path or path length. And so the concentration is going to be equal to 0.70 divided by 8,400 times 1. And my concentration then works out to be 8.33 times 10 to the negative 5 mole per dm cube. And with that, we have come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right here, you'll find our Module 2 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So, thanks for watching, and we'll see you in our next video.